the inverse tangent of x, quantity squared, that's with respect to x, and then that's over x squared plus 1. Okay, guys, now they told us that u is equal to inverse tangent of x. Hopefully you're saying, we don't need them to tell us that. We knew that in this problem. Because we say, let u be whatever's inside of a function. We see that this is inside of an x squared function. And then the nice thing, if we let u equal inverse tangent of x, hopefully you remember your Calc 1, the derivative of inverse tangent is 1 over 1 plus x squared dx, which is what I have here. So I can say du is equal to 1 over x squared plus 1 with respect to x. So this works beautifully, and I can say this is going to be the integral of, I know this 1 over x squared plus 1 dx is all du. The only other thing in there is the inverse tangent function squared, so that becomes u squared du. That's what we do. So we say the integral of u squared, I can't stop myself. The integral of u squared is u cubed over 3 plus c. So we can say, now substituting back in for u, this is the inverse tangent function cubed over 3 plus c. Final answer. That one was not as fun as I thought it would be. Looking at the set of problems 27 through 72, let's look at number 66 looks fun. It's the integral of secant squared theta. And if you happen to see one in here that you think looks more fun than the ones I'm choosing, please let me know. We'll work any of them in there. I want you to be confident that if you look at any problem in the book, yeah, we know how to do that. There shouldn't be anything in here that we don't feel confidence in working. In this one, it doesn't tell us what to let u equal, nor should it. Is the choice for u obvious in this case? You say, well, from Calc 1, I remember derivative of tangent is secant squared. So if I let u equal tangent theta, du is secant squared theta d theta, beautiful. So that's what I'll do. So now in going in here, and I think last class I might have mistakenly called this trigonometric substitution. This is substitution, integration by substitution that happens to involve trigonometry. It is not trigonometric substitution, which is more fun and harder than this. So we're going to get to that very, very soon. Whenever I integrate this function, I see everything that I'm going to underline is du. Okay. Everything else, well, that's going to be e to the u du. The integral of any exponential function is that exponential function divided by the derivative of its exponent. Derivative of the exponent in this case is 1. So we just get e to the u plus c. Final answer, e to the tangent theta plus c. You see? 72. Perhaps, oh, I like 72. I like it. I recall working a problem similar to that. It's the cotangent of x. I think I might have pulled this problem out from my other examples, maybe, because I looked at it and liked it so much. Natural log of sine of x. So we may have worked this problem because it looks familiar, and it's a wonderful problem. So whenever you're looking at this one, you'd say, well, okay, there's no way I would let this be u, because derivative of cotangent is going to be negative cosecant squared. That's nothing over here from that. But I know derivative of sine is going to be cosine, And the cosine is there because this is understood to be cosine over sine. So I can say, okay, I can work with that, I think. And I'll say, let u equal the sine of x. So du, derivative of sine, is cosine x with respect to x. And then I can say, well, this integral could have been written as cosine x over sine x, natural log of sine x dx. Now, I know that I'm going to cross everything out that's going to be replaced by du. Cosine x dx, cosine x dx is going to be gone. But I'm still going to have that 1 over sine x. Well, sine of x is u. So I'll say, well, okay, this is going to be the integral, 1 over u, natural log of u du. Okay. And this is the point where you say, well, how do I integrate the natural log of u over u with respect to u? And if you want to stop it, John, at this point I would look at it and say, well, I could do another substitution. This isn't the only way, but it's a way. And so the double substitution, I'll say, let's let w. I'm going to let w equal the natural log of u. Why would I do that? Because in my head I'm already thinking, well, the derivative of the natural log of u with respect to u is going to be 1 over u. That's nice. I have a 1 over u in the problem. So I'll let w equal the natural log of u, and then dw is going to be the 1 over u with respect to u. So now I know all of this becomes dw, and I'll have, this is the integral of natural log of u is w, so I have the integral of w dw, which now we can finally integrate pretty easily and say that this is w squared over 2 plus c. And then if you say, well, what do we do from there? Back substitute. So you say, well, w was equal to the natural log of u, so this is going to be the natural log of u quantity squared over 2 plus c. And then back substitute one more time. U is equal to the sine of x, so our final answer is the natural log of the sine of x, all of that quantity squared over 2 plus c. I would say that problem increased the fun factor. I would. In the definite integral part, problems 79 through 90. If you want to look through some of those, let's see, we'll look at one algebraic and then one trigonometric. So 86 and 90, for example. In looking at number 86 in 5-6, we have the integral from 10 to 17. And then on the inside of our integral, it's the rather innocent looking function x minus 9 to the negative 2/3 power dx. This is not a problem in which we would actually be required to use substitution. The reason I'm going to is that's the point of this section. So I'll say, well, okay, I'm going to use substitution and the change of variables formula like they suggest. So I'll say, okay, let u equal what's inside the function. So u is equal to x minus 9. U equals x minus 9. Du is simply dx. And then you'd say, well, if you're going to change your variables, I can't say my limits of integration are from 10 to 17 anymore, because please remember, this is with respect to x. So you could literally say this means x equals 10 to x equals 17. I can't keep my limits in terms of x when now my problem is in terms of u. So I would say, well, what is u is a function of x, you solve in terms of x, so what is u of 10? U of 10 is simply 10 minus 9, 1. U of 17 is simply 17 minus 9, or 8. So we'll say this becomes the integral, instead of 10 to 17, 1 to 8, and instead of the group x minus 9 to the negative 2/3, we just have u to the negative 2/3 du, since dx is du. Now we integrate, we know we add 1 to the exponent. U to the negative 2/3 plus 3/3 is u to the 1/3. Divide by that new exponent. If you divide by 1/3, you're multiplying by 3. So I'd say 3u to the 1/3 evaluated from 1 to 8. That works great because we can see when we plug in the 8, it's the cube root of 8, which is 2. 3 times 2 is 6. When you plug in the 1, I'm just saying cube root of 1 is 1. 1 to the first, still 1. Times 3 is 3. So 6 minus 3, 3 is what it would be.
Do you have to use u substitution on that problem?
So to answer that question, no. But why did I? Because the section told me to. But you're right. As soon as I saw this, you could just say, well, this is the group x minus 9 to the 1/3 times 3, just by looking at it, and then evaluate from 10 to 17. So substitution is not required on this problem, but I would say within this section it was, because the point of this section is substitution. Yeah, Clint, I would say what they needed to do is put a harder problem than that, because substitution's not needed on that. If they wanted us to have to use substitution, they should have made us use it. Number 90. Let's see if they make up for it on this one. It is wonderful trig, so that's a good thing. Pi over 3 to pi over 2. And it gives us cotangent squared of x over 2. And then cosecant squared x over 2 dx. Okay. So we always say we let u equal what's inside of a group. I actually have quite a few groups. One u substitution that would not be enough, because you just have to do another u substitution later. One trivial one you could do is say, well, let u equal x over 2. But I guarantee you, you're not going to be much better off, because you still have cotangent squared u, cosecant squared u du, and you'd have a factor of 1/2 out in front. Not going to help a whole lot. So I'm going to go ahead and say, well, I know each of these are inside of a function. This is the cotangent group squared, the cosecant group squared. When I think derivative of cotangent, negative cosecant squared, the derivative of cosecant is negative cosecant cotangent. Actually, either of those would work in this case. I think the easier one is going to be if I let u equal this one. But even if I let u equal this, the derivative is still there. But the problem is that that first term, you're only going to get rid of one of the powers of it. You're still going to have a cotangent floating around if you let u be this. That wouldn't be the end of the world. We could get rid of it, but this will be the easier method. And we're all about doing it the easier way. So we say, okay, let u equal the cotangent of x over 2. Now, we remember, okay, derivative tangent secant squared, derivative cotangent, negative cosecant squared. So I'll say du is equal to negative cosecant of that angle squared. Am I done? Times the derivative of the angle. Well, you can think of that angle as 1/2 x. So the derivative of the angle is 1/2. And then, can't forget our dx. Okay. So now I know that I need to see everything in there. I already see most everything in there. What I don't see is a negative 1/2 times the dx. So what I'll do is I'll go ahead, instead of rewriting the problem, I'm just going to go up to the original and say, I need a negative 1/2 on the inside. If I multiply the inside by a negative 1/2, I better multiply the outside by negative 2 to make up for that. Okay, so now the problem is just as it was. In this same step, though, I'm wanting to do a u substitution. In order to do that, I also need to change my limits of integration. So I'll say, well, what would u be if I evaluated it when x is pi over 3? Cotangent of pi over 3 divided by 2. That's going to give me cotangent of pi over 6. And guys, this is where, if you haven't memorized your unit circle, please do so. It makes things so much easier. So I'd say, well, if I'm at pi over 6 on the unit circle, what I'm supposed to know is that means the x value on the unit circle at that point is the square root of 3 over 2. The y value, the sine, 1/2. So I could say, well, I know cotangent is cosine over sine. So the cotangent of pi over 6 is the square root of 3 over 2 over 1/2. So I'd say, well, this is square root of 3 over 2 over 1/2. When I divide by 1/2, I'm multiplying by 2. The cotangent of pi over 6 is just the root of 3. Okay. Now, what I would say in a problem like this is exact answers only, to avoid someone just saying, well, I can type that into my calculator. No, that would be cheap. I want you to get an exact answer. Nice. So now we'd say, you evaluated at pi over 2 is just the cotangent of pi over 2, cotangent pi over 4. We should know that pi over 4 is the point on the unit circle, and anything over 4, your sine and cosine are always the same absolute value. So it's always going to be 1 or negative 1. At pi over 4, it's 1 because we know both the x value and y value component. The x value is going over less, the y value is going up more. Square root of 2 over 2 for both. So I can say the cotangent, cosine over sine, 1. That means, now that I have this set up, this problem changes to negative 2 times the integral. The lower limit of integration is the square root of 3. The upper limit of integration is 1. So we're actually going backwards now from square root of 3 to 1 because placing it into our formula gave us this direction. Cotangent squared x over 2, we know that becomes u squared. Everything else here, negative 1/2 cosecant squared x over 2 dx, all of that is du. So every bit of this gets replaced with a du. So now the integration is pretty easy. And we say this is going to be negative 2 times the group, u cubed over 3, evaluated from the root of 3 to 1. So I'll say, well, okay, it's going to be negative 2 times. When I evaluate this at 1, I get a 1/3. When I evaluate it at the root of 3 cubed, I know the root of 3 times the root of 3 is 3.